Hamdi began his academic journey in 2000 with a civil engineering degree in meteorology, followed by a master's degree from Catholic University of Louvain, Belgium in 2002. After completion of his PhD in urban meteorology in 2005 from Institut d'Astronomie et de Géophysique J.H. Lemaire, Professor Hamdi has been an integral part of the research department at the Royal National Institute of Belgium. His work with the international consortium ALADIN, specifically on the development of Alaroth atmospheric model and the surface land surface scheme, has been groundbreaking contribution to both numerical weather prediction and urban climate modeling. Professor Hamdi is also a member of prominent international organizations, including the International Association for Urban Climate, IAUC, and Urban Climate Change Research Network, UCCRN. He further served as a lead author for Intergovernmental Panel of Climate Change 6th Assessment Report, IPCC AR6 in 2021, and the Summary for Urban Policymakers, SUP, IPCC report in 2022, demonstrating his pivotal role in shaping global climate policy discussions. Beyond his research, Professor Hamdi has been deeply committed to academia, serving as a guest lecturer in Ghent University since 2014 and a guest professor at the Chinese Academy of Sciences since 2023. His mentorship of PhD, master's, bachelor students highlights his dedication towards nurturing the future leaders in climate science. Professor Hamdi's extensive body of work includes securing funding for 13 research projects, co-authoring more than 100 peer-reviewed publications, and contributing to 20 book chapters. His expertise has also been recognized in practical applications, such as his role as an urban climate expert on the scientific committee for the 2024 Paris Olympics. Today, we are privileged to have Professor Hamdi with us, who has traveled from Belgium to share his unparalleled knowledge and insights. His work on regional climate modeling, urban meteorology, and the impacts of global warming on urban environments is invaluable as we confront the challenges of a rapidly changing climate. It is both a privilege and an honor to host a distinguished scholar and a globally renowned expert, Professor Hamdi, whose contributions have significantly advanced our understanding of urban meteorology, climate modeling, and the critical dynamics of urbanization and climate change. Sir, I would request you to please address the gathering.
Thank you very much for the very nice introduction. And good afternoon, everyone. Good afternoon also to the online participants who are joining us also. So, I am very honored, and I would like to thank again Professor Sorabji for her invitation, very kind invitation. So I am deeply honored to be here for the first time in India. So I am happy to explore also India and also the wonderful people that you are. So my lecture will be this afternoon divided into two parts. So the first part, because I discussed a bit with Professor Sorabji, we said, okay, maybe it's good that we give you like a general introduction. So what is climate change? What is this problem from the beginning? Then in an easy way. And then the second lecture will give you what is the state of the art, what we know now on climate change from the latest report, IPCC report. So here it's my first lecture, so it will be 1 hour, then we take a break, and then we go to the next lecture. Okay, so yes. So maybe next slide, please. Yes, so the first thing that I need to say is that the climate is very complicated. It's really a complicated discipline because you need to know meteorology, you need to know oceanography, physics, glaciology, biology, mathematics, numerical modeling, because you need to run with supercomputers, so you need to be very good in this, and also how the infrastructure is evolving. You know that now we are moving from CPUs to GPUs, so some code that we are using is no more adapted to GPUs, so we need to adapt our code. Very, very, very important. economy and technology, because this is related to your question, how in the future the economy will change and how this will change urbanization, how this will change the behavior of people. So you need to link economy, technology, socio-economy also. So all these disciplines you should to know to make the good scenario projection in the future. And how this affects the emission, you will see. So climatology is an applied science. So it's not an exact science because you need to know all this and you put this all into one, you combine all this. So what I would say is that no one can master this. You can never find one person who is able to do all this, including me. So it's normal that if you ask me a question, maybe I will not be able to answer because maybe this question is related, maybe your question is related to this. I am not expert on running this future projection. I just use this future projection. Maybe you have a question glaciology, but I am not expert on glaciology. So you see, it's really very difficult matter, this climate. Next slide, please. And the most important is that climate change is a hot issue because we need to provide guidelines to policymakers. Policymakers, this is what has been said this morning. They need solid science from us for the policymaker. And also, the policymaker, we need to change our way of talking with the policymaker. It's not that we scientists, we have the knowledge and we give this to the policymaker. It is not working like this anymore. We need to set up a dialogue with them. This is what has been shown in the lecture of Professor this morning, Subal, yes, about how they involve stakeholders in the map. Did you see you remember the map that the application, the application that he showed? He said that there is a feedback and interaction with the stakeholder. It's not only one time. You need to set up the dialogue and then interact with the stakeholder because they might need some information that from you don't know that this is important, so you don't save it in your output. But then later it becomes important. So it's a dialogue and it's an iterative dialogue with the stakeholders in order to and you need to start from the beginning. So it's not that you are doing your research in your corner and then you said, look, I have some. No, it's not working like this. For climate, you need to involve all together from the beginning. Next slide, please. So let's start from the beginning. So why we have this? What is the climate? What is happening to the climate? So the climate. So the Earth, the climate of the Earth is what is influenced by the forcing. Okay, so we have the forcing, and climate forcing. What is the most important is the radiation. Okay, so the radiation which is coming to the Earth is the only way the planet interacts with the rest of the universe. So it's the radiation. So this radiation is then converted to heat. Okay, and then this heat is then converted to kinetic energy, which is momentum, so the wind. Okay, so the atmosphere can be seen as an engine, or if you wish, you can call it a heat pump, and this is explained by the general circulation. So you have the Earth, you have the radiation which is coming, and this radiation heat the atmosphere. The atmosphere is circulation. We call this the general circulation, okay, which include like monsoon, also, and all this stuff. This is general circulation. So the climate can basically change for two reasons only. The first one is change in the incoming radiation. So this radiation change. If the radiation change, okay, the climate will change. Or a change in the mechanism for the energy conversion. I told you, radiation converted to heat, heat converted to general circulation. So if this mechanism change, then the climate change. So the only two ways the climate change is radiation or change in the mechanism. Next. So what is so you all heard about this greenhouse. What is the greenhouse effect? So I will start from the beginning. Then we are all clear about what is greenhouse. What is this problem of greenhouse? So suppose that there is no atmosphere in the Earth without any atmosphere, and with an optical thickness, the terrestrial radiative emission should be equal to the absorbed sunlight. Okay. So this is the radiation that we get from the sun, okay? So you remember here, PR is because it's spheric, because the radiation on a spheric is this, And this is the radiation, this is the constant, and this is the albedo. I will explain what is the albedo. And this radiation should be equal. What is this? This is the emitted, it's the Stefan Boltzmann emission. So this is like if you have a black body, this is how it will emit radiation. So this is how, so if this is the Earth, temperature of the Earth to the power 4. So if there is no atmosphere, the radiation that will come will be output by this law. That's very easy. So if you compute this, this is the constant solar radiation constant. This is constant. You will see it has a cycle of 11 years, but we can consider it constant. And this is the albedo. What is the albedo? This is 0.3. It means if you have solar radiation, part will be reflected. Part of this solar radiation. For example, if you have a snow, snow is white, a lot of radiation will be. So this is the albedo. Albedo of snow is very high. But if you compute the albedo of the Earth, is 0.3. Okay? And TE is the effective temperature of the Earth. Okay? So the solution of this is very easy. You will find that temperature is 255, which is about minus 18. So if you don't have the atmosphere, the temperature will be minus 18 degrees. So, but hopefully we have the atmosphere. That's why we cannot live with this. An average. Can you go to the... So why we don't have minus, why we have, the average temperature is 15. So why we have 15 degrees on the Earth? Because of the atmosphere. The explanation lies in the optical thickness of the atmosphere, this heat the atmosphere. So you have the atmosphere, and this atmosphere heat the Earth, and then we have a temperature of 15. So it's a greenhouse effect. So the greenhouse effect in the atmosphere is a changing in the radiative equilibrium. So remove the atmosphere minus 18 degrees, put the atmosphere 15 degrees. So you see, it's a greenhouse. So the greenhouse changed the radiative equilibrium of the Earth. Next slide, please. So the radiation basically, so I will not enter into details, but just general. The radiation, you need to think of two types of radiation. These are the most important. You have the visible and you have the infrared. We call this mid-infrared. So the visible is this, like during the day, the sun radiation. The radiation, this is visible, okay? So it is in this band. This is the spectral band of this radiation, visible, like today, in the day, you have solar radiation, visible, in the visible, mostly in the visible. During the night, when we have Earth, cooling of the Earth, this is more infrared radiation. So put it in your mind. In the short wave in the day, infrared mainly in the night. The most you have also in the day, but the most important is in the night. Next slide. So this graph, what is this? So here in blue, this is what is this long wave emission. I told you in the night you have long wave emission from the Earth. So the blue is what is emitted. This is the radiation which is emitted at the surface. So at the surface here, and in red is the top of atmosphere. Top. So you have the atmosphere, you have and then you have the top of the atmosphere. Okay. So we compare between the surface and the top. You see that here that's more or less okay, but here you see that we have reduction. Reduction. It means that it's absorbed. So this is absorbed by CO2. So CO2 absorbed in this band. In this band, CO2. You see a little bit also here. Water. Water is a greenhouse gas. Water. You have also ozone. In this band, ozone absorbs a lot, but it's more higher troposphere. Okay. So the greenhouse gas, because we always talk about water vapor. We always talk about carbon dioxide. We say carbon dioxide is greenhouse gas, but the first one is water, in fact. The water, and then carbon, and then other gases. So next slide, please. So now let's look to the visible. So during the day, short wave. So this is the short wave radiation, and this is the altitude. You see here, 10 kilometers of the atmosphere, 10 kilometers, and then you go up. So the blue is for the water. You see that the water here is absorbing. So this is at 5 kilometers, you have maximum of absorption. So this is how much degree per day. So the water is absorbing the visible. So it will heat. Okay. Now look to the CO2. CO2 is in green. So the CO2 does not change. So it means that for the visible radiation, during the day, for example, when it is coming to the Earth, okay, the CO2 will not affect. You see, CO2 is exactly the same. So the radiation will not change. So it will not heat the atmosphere. The CO2 is what we call the here. So different CO2 is transparent for light. So if you have light coming, the fact that you have CO2 or not will not change the atmosphere because CO2 is transparent for light. Okay. Next slide, please. Okay. So now, so we say that we have this increase of temperature which is due to the greenhouse gas, but it is generally believed that the increase in temperature depends logarithmically on the concentration of greenhouse gas. So here, this is the like the concentration or initial concentration, and then you increase the concentration. The temperature is a logarithmic way. So it means that it will increase this way. It means that since it is logarithmic, the more you add greenhouse gas, the temperature will not warm that lot. So one could say the more we add greenhouse gas to the atmosphere, the less they will have a greenhouse effect. Normally, this is what should happen because it's logarithmic, okay? But in fact, the sensitivity without feedback of carbon dioxide is about 1.3. So in fact, if we don't consider the feedback, okay, if we just add a greenhouse gas to the atmosphere, normally if you add, your atmosphere, you will heat, the temperature will increase by 1.3 degree. Okay? But this is not what we are observing. So because you have feedback. And I will tell you what is this feedback in the next slide. So the sensitivity, so just put this in your mind. The sensitivity without feedback is 1.2 or 1.3 degree. Okay? So why we are talking about climate change and the problem of climate change? Because it's only 1.3, but no, because there is feedback. The feedback you will see which will put the warming much more than 1.2. The next slide, please. So, of course, in the atmosphere, we have the feedback. This is what I told you. And one of the feedback is the urban. You have the surface that have a feedback with the atmosphere. And you will see this is for the urban is one example. So the net sensitivity is not 1.2 or 1.3 because of the forcing, because of the feedback. If we don't have this feedback, we don't have any issue with climate change. But because of this feedback, then it becomes really an issue. Next slide, please. Okay, so one of this feedback, it's the surface feedback. So because the surface, here if you have vegetation or if you have city, the surface is interacting with the atmosphere. So this interaction is via some exchange. So you exchange water, you exchange heat between the surface and the atmosphere. So this make a loop. For example, I will give you an example. So suppose that you have a warming over warming so the temperature increase. Okay, this temperature increase will make a lot of evaporation. Okay, from the soil because temperature increase. So more evaporation. This will make your soil dry, right? So the soil will be dry. So in the next step is that the soil, since it is dry, it will be warm because you don't have evaporation to cool down. So the temperature will be more warm. And then this is a loop. You see? This is the feedback. So the feedback will with the surface. Next slide. So yeah, this is what I already said. The surface absorbs and reflects sunlight, and it also emits long-wave radiation. This is we know. And the reflection is called the albedo. So this I told you about this. And yes, so this is just to give you some. So this is for the average, and you see here, for example, the albedo that I told you with the surface. For example, for snow, it's different between old and fresh. You can have the fresh, very white. You can have 0.8 albedo, while the old one 0.4. So it's a feedback, because if you have a warm temperature over snow area, it's not the same like you have a warm temperature over a dry area. Because also if you have a more solar radiation over snow, it's not the same like you have more solar radiation over a dry area, because the snow will reflect. So the snow will reflect, so you will have different process over different type of area. So that's why the surface feedback is very important. It's one of the feedback that it's very important to take into account. Next slide, please. And yes, and another type of feedback is, because it's about urban, is the urban heat island. Because the fact that you have city is different from the fact that you have a rural area or forest. One very unique aspect of city, what is the very unique aspect of cities? That you don't have anything. Yes, but you can say, but for the atmosphere. What is unique that the city is giving to the atmosphere, which other type of surface is not given to the...
More favorable surface, so reflection of the radiation.
Yes, all this, but it's the anthropogenic heat. Yes, the anthropogenic. Because you can have, for example, you can say, okay, city is affecting the wind, but forest is also high. So the wind is also will be reduced. You can say city is warm, but you can also have, for example, during the night, water body is also warm than the dry. But the unique, very unique, that you don't find is the anthropogenic heat. You don't find this in forest or in lake or so. So this is very important. So all this feedback should be taken into account for the. Yeah. But this I will, because the urban we will have this more and more. All this I will not go into detail in the urban. Next slide, please. Yes, the other feedback. So we said the feedback surface. Okay. The other feedback is the aerosol. What is the aerosol? Do you know what is aerosol? You know what is aerosol? Yes. Yes, so the aerosols are these particles that are suspended in the air. You don't see it, but they are here in the air. And this can be dust, sea salt, soil particle, volcanic, pollen, etc. And you see the size are very small, very, very small. And they are almost, but what is particular in this aerosol, they are not staying in the atmosphere for a long time. The CO2 has 100 years, flies. But these aerosols, 3 days, they stay 3 days because they are coming back by rain. So they don't stay in the atmosphere, and we call this what we call it's here. It's short lived. So it should be somewhere here. So we call this short lived because they are not in they don't stay in the atmosphere for a long time. Okay, and they are very important because they form the nuclei for the cloud formation. So if you don't have aerosols, it will be difficult. That's why we heard this morning about the effect of urban on precipitation. One of the effects, Professor Subimal showed this, is the aerosol. Because the aerosol can increase the precipitation. Because you have more aerosol, you have more precipitation. So the aerosol is very important. Because yes, they are very important also for radiation, for absorption and scattering. Because if you have aerosol, and you have radiation, the fact that you have aerosol will impact the absorption and the scattering, okay, of the radiation. For example, but we will see this, I think, in the next slide. Yes, next slide, please. Yes, here. So this is to measure how much of aerosols. We call this optical depth, but don't worry about it's just a measure of how much we have aerosols in the air, and this is in Uccle, in Brussels, okay? And this is from 1982 to now. What we saw is that there is a decrease of aerosols, okay? Because of all this air pollution condition, so we limit the emission, etc. So we have the aerosols which decrease. So if you have a decrease of aerosols, and you will see in the next lecture, normally aerosols make a cooling of the atmosphere, and you will see in the IPCC that the aerosols make the atmosphere cool. So it's a cooling of the, it's not a warming. So with this decrease, in fact, we found that, for example, in Europe, the summers of Europe are more and more extreme because we have less aerosols, then you have more solar radiation coming to the ground. Because less aerosols mean you have more radiation and if you have more aerosols, you have less radiation because all is scattered, so less radiation, so it's cooling. It's cooling the surface. But we found that over Europe, for example, the fact that we decrease the aerosols is good for the health, but it makes the summers more and more extremes in Europe. So it's kind of, yeah. Next slide, please. Okay, so if the atmosphere increase, there will be an, yes, the other feedback, so we call the surface feedback, the aerosols, and the other feedback is with the water vapor, or what we call the cloud. It's very important. The fact that you have cloud will change everything. So if the temperature increase, okay, then there will be an increase of water vapor in the atmosphere, okay? So if you increase the temperature, you have more evaporation, so you have more water vapor in the atmosphere. So we saw that the water vapor is a greenhouse, right? We saw this I show you this. So if it's a greenhouse, so it will make more hot. So if this water vapor does not condense to form cloud, if it stays water vapor, then it will enhance the greenhouse effect, okay? And this in turn will enhance the temperature and so on. So you see the feedback? So you have a warm temperature, more evaporation, so you have more water vapor in the atmosphere. This will be more because it's a greenhouse. It will make temperature hotter, and you see this is a feedback also. So you remember that's why we don't have 1.2 degrees Celsius of, this is without feedback.
Sir,
Yes?
it is beyond going to 1.2 to 1.3, so that will create a problem, or it is a standard? That you have said that the feedback 1.2 degree between 1.2 to?
Yes, normally this is without all this feedback, yes.
So it is, I think it is a standard, atmospheric regular procedure.
Exactly,
like
yes.
cybernetic system.
Yes.
So what will the problem arise? Beyond the 1.3 or?
No, this is the 1.2 or 1. This is if there was no feedback. This is just a theoretical. We say, okay, if we have an atmosphere where we put more greenhouse gas, what will be the temperature? Will be because it's logarithmic. But the atmosphere, it's very complex because you have all this feedback that impact the temperature. So it's not only adding greenhouse gas warming, but this, for example, if you warm, the process will change, all this feedback.
So any standard, natural standard of the temperature about, like you said, 1.2 or 1.3 or beyond that? You know, I mean to say, lots of anthropogenic activity is going on in
Yes.
cities and urban
Yes.
areas.
Yes.
So nature has itself any specific temperature to
The next equilibrium.
type of activity.
Yes. This is what we will see in the next slide. So what is the equilibrium state that we will reach? Yes, this we will see in the, yes. So, yes. Okay. Yes, so but this matter that I show here with the water vapor, it will be more complicated if you have cloud. This is just without cloud, because if you add cloud, then the amount of solar radiation will decrease because you have cloud. So less solar radiation will, so it's much more complicated. But yeah. Next slide, please. Okay, so yes, then you have cloud feedback and aerosol. So the cloud feedback can both be cooling or warming. Yes. So for example, I give you an example. During the night, if you don't have cloud, okay, the night will be cool. Why? Because all the infrared emission can go to the air, okay? Yes, so cooling, you have a cooling. But if you have cloud during the night, a lot of this infrared will come back because they are reflected by the cloud, okay? So your night will be not that cool, will be not that cold because you have the cloud feedback. So you see, or it can go to cooling. For example, during the day, if you have cloud and you have solar radiation, so you have less solar radiation because it's cloudy, of course. So then you have less temperature during the day. But if you don't have cloud, like today, then it's warm. But if you have cloud, it's cold. So you see, the cloud is different. It can affect in different way. So that's why we need really, for all the atmospheric model, the climate model, we need to have a good parameterization of microphysics. So if you have a good parameterization, then your model is good. So here is all the feedback, but I don't want into. Next slide, please. So this is why we need what we call AOGCM. This is Atmosphere Ocean Global Circulation Models. Okay? So you need, if you would like to study the climate, you need atmosphere and you need the ocean. The ocean is very, very important also. And then we can reach, if we have a good model, like this, then we can reach what is, if we put more CO2, what will be the next radiative state? This is your question. What will be the temperature? So, but we need to have a good model first that take this into account. So this is what I say. The sensitivity without feedback of CO2, if you change only the CO2 without any feedback, is about 1 to 2 degrees, okay? But in reality, the sensitivity will be different because, and the problem for this are the feedback that I just explained you between the surface, aerosols, cloud, all this, okay? So the only way really for now to estimate the net sensitivity, your question, is to include all the process that we know into the model, into the atmosphere and the ocean, and carry out sensitivity tests. So we try to have the best model we can have. We put all the process that we know, and then we run the model to see what is the next state. If we add more CO2, what will be the temperature? Because we know that this is not good. This is not correct, okay? So this is why we need this atmospheric ocean general circulation model. But here in these courses, I am not expert on the ocean. So you see, already I told you, you need to be expert on ocean. I am not expert. So we just use the model. But here we will focus on the atmosphere. Next slide, please. So I will not enter into detail. These are the equations that, what we call the primitive equation of the atmosphere. Okay, so you need to understand all this, and we put this into numerical model. So that's why I told you, you need mathematics and physics. All this is mathematics. And next slide. So what we do, so here, for example, is the Earth. We try to make a grid over this Earth. Okay, so like all these points here are the grid point. Okay, we have a mapping of the Earth, and you see that since we will have a mapping over all the Earth, the resolution. What is the resolution? Is the distance between 2 points. Distance between these 2 points is the spatial resolution, let's say. So since it is very, of the Earth, normally it's very coarse. So for example, now I will show you the model of IPCC, which resolution, but it's around 100 kilometers. You see, 100 kilometers is too coarse. You cannot, city, for example, the cities, they are not seen by the global climate models. I will tell you about this. So, and then we discretize. So all these derivatives that I show you, the derivatives are replaced by finite difference or other method. You see here the numerical technique is very important to put all this equation into a model. You need to know, is it this? This is the numerical technique, which are now very challenging because I told you we are going from CPUs type of computing to GPUs, graphical. This is the new way of doing the computation. So all the method that we make until now should be adapted to this new. Next slide, please. Okay, so you have a mapping over the Earth surface, but you need also the vertical level. Okay, so you need to map to have a vertical level all over the atmosphere. For the moment, we are having, like, for example, 100 level. And it's better if you run climate model to have a lot of levels near to in the boundary layer, like from 0 to 3 kilometers. It's better to have a lot of, as much as possible, of atmospheric level, because then you can resolve all the process that are happening in this. So here we are using this type of variable of sigma. So you see our this variable that we are using, it follows the surface, but then upper air it's constant, because that's why we assume that in the upper we don't have a lot of process. So but in the surface, so it's following the surface. It's very important that your variable, that your layer is following the surface, that you can understand orography, all this aspect of the surface. Okay, next slide, please. Okay, the third one is the time stepping. Okay, so the first one is the surface grading, the vertical, and then from one time step to another time step. So this is very important. So you need to have a initial condition, and a boundary condition, and the most important is the stability. This is very important criteria, and I will tell you why. Because you need that you satisfy this, at least. What is C? C is you can consider it like the speed of one process, of one phenomena you are interested on, okay? Delta T is the time step of your model, and delta X is the spatial resolution. So you need to satisfy this. That's why, for example, it will be good if we can run the global model with very long time step. It's much more easy. Then it's very fast to make the computation, to finish the computation. Just to give you an example, one global climate model need 1 year of run to do the IPCC runs. So you need 1 year, really 1 year of running. So you see, it's very time compute. Why? Because your delta T must be less than 1 delta X divided by C. Delta T must be small because we are always, I would like to run with a time step of 1 hour or 1 day. But because then it will, because all the grid point I show you, you need to run your model for all the grid point that I show you, and also all the vertical level. You can imagine the number of grid point that you will run. So the best, the longer time step, the best, but we cannot because of this condition. So the time step should be less. If not, your model will crash. Your model will not work. So this is also very important. That's why it takes time. Computing simulations really take time. Yeah. Okay, so you have your dynamic. We call this the dynamic model. Okay, the wind you put all into. You have your grid, your vertical, but then it comes all the physical parameterization. So you need to put all this physical parameterization in your model. So this is what I told you. In order, if we would like to estimate a good feedback that I told you, you need to have all this feedback: radiation, convection, turbulence, all this, surface interaction, urban here. Also, you see, I put urban. Next slide. Okay, so and then you have another problem, is because I told you, global climate model, you need to run over all the Earth, and the spatial resolution is very coarse, 100 kilometers, for example, for the moment, 100 kilometers. Everything which is within the 100 kilometer, this will not be seen by the model. Okay, so that's why, if for example someone is interested by cities, okay, and then go to the global climate model, CMIP6, for example, CMIP6 will not give you what is happening in Bhopal, because they don't see Bhopal as a city. They see maybe Bhopal, maybe it's lake, maybe it's a forest, or because they don't see what is happening. So it's very difficult to get useful information from global climate model for a city, because the city is very. Do you know what is the percentage of city, of urban area in the Earth? Give me. How much you think the city, the urbanized area, are on the surface? What is the percentage?
3 to 4% area.
How much?
3 to 4% area of global.
Yes, less than 2. Less than 2%. You see, all the cities is less than 2% of the surface. So the global climate model, they don't care about cities. We don't care. It's less than 2%. We will not put anything because they don't care. But we are all living in cities, so we need to know, and the stakeholders need to know impact of climate change on cities. So it's difficult to get this information because of this problem. Next slide, please. Another problem is the deep convection. The deep convection, because you have, this is very important, precipitation, intense precipitation also. Like global climate model cannot see this because it's 100 kilometers, and this is really much more less. So you need to parameterize this. You need to add all this. You need to estimate the impact and put it into the global climate model, because the global climate model have a coarse resolution, this climate. Next slide, please. Yes, maybe another example. This is for city, just to give you an example. So suppose that this is how your model, this is Belgium. Huh? Belgium here, you have London here, UK, Paris, and this is Belgium here. So we are running at 4 kilometers, because then your model can start to see the cities, okay? This is not a global model. This is a local climate model. I will tell you about this later. So, but then this is how much of calculation you need, okay, for this domain. It's 4 kilometer domain. Now, if you would like to see this city like this, you need a computer 10 to the power 10 faster. Why? Because the time step, see, the time step should be much more less because you are running at high resolution. So the time step is much more less because of the condition that I told you. If not, the model will not. So you see, you need a computer much, much more powerful. But we don't have this for the moment. I just put this 10 to the power 10 faster, and we cannot do this. So that's why we need to parameterize. Next slide. please. We need to parameterize, but this I will explain you this I think tomorrow or the day after tomorrow, how we put cities into the model. So you can go to the next slide. Yeah, this is how we parameterize the city. So it's really like a canyon, but I will explain you this later. You can go to the next slide. So okay, so you have all these global climate models, okay, but the problem is that I told you subgrid process. The subgrid process, like convection, I told you, like urban area, like everything, are not solved by solving the equation of the nature that you have. So they are estimated. All these subgrid, they are estimated, okay? And these estimates involve some parameters that have no equivalent in nature. For example, what has been shown by Sobimal this morning about the effect of CT on precipitation, they found that when they put multi-layer, it's linked to the turbulence. The city will make turbulence, and this turbulence, okay, will interact with the wind, etc., and will make the precipitation correct, intense precipitation. So all this turbulence, because we are not running at high resolution, we run at this coarse resolution. For example, for the turbulence, we use what is called turbulence eddies. We use this mixing length. The mixing length, it's not in the nature. You will not see a mixing length in the nature, but we just put this into the model like parameter. Huh? We think theory, okay, we will use this parameter, but this is meaning we will use certain parameters, tuning parameter, okay, some tuning parameter, and so this is the issue of parameters. So such parameters are then chosen to make the model behavior as performant as possible. Of course, we compare with the observation and we try to have our model as best as possible. That's why you can ask me why we have 30 global climate models or more. Why? Because the equations are the same. What is different is this process. So every model make differently how to make the subgrid process. You see, so for the radiation, every model have their subgrid process. For the convection, that's why you have different schools. You have one school doing this type of parameterization, another school, and both are correct, but they are different. So that's why we have different global climate models. This is the reason. Next, please. Okay, so then we do this sensitivity to answer to your question. If we put more CO2, how much? So for instance, in greenhouse gas, so we make a model run sufficiently long to reach an equilibrium state. So we run, once we are happy of the model, we run the model for a long time until it reaches the equilibrium, and then we check, okay, the temperature is 4 degrees. The temperature now of CO2 is 4 degrees or other. And then, yes, this is what, we double the concentration, we put double, and then we make sensitivity, secondary, and then we make a sensitivity and take the difference in global surface, and we compute for the Earth. Next slide. Yes, that's why. So we have more. It's not 30, more than 30 for the IPCC 6 assessment. I think we have 50 or 50 global, but all these models are they have different dynamical core. And also, the most important, different physics parameterization. Every model has its own physics parameterization. That's why we have different models. Okay, next slide, please. Okay, so I told you about the model. Now, maybe very fast about the observation. So, how to observe the climate? Okay, next slide, please. What we use to observe the model, to observe the climate, is we use what we call weather station. So the weather station is this type. This is a picture in our station. So it's this type of station where we have like we can observe temperature, wind, relative humidity, and you have a good coverage globally of this type of, yes. So this is the type of observation. So generally it is between 1.2 and 2 meters above the ground that we put. And yes, what is important is that the distance should be 3 times the height of the obstacle. So this type of observation should be far from obstacle. This is why we don't have observation in cities. Because we are not allowed by the WMO, World Meteorological Organization standard, we are not allowed to put this in cities. But now, the problem, this is what has been shown also this morning, is that we need observation in cities if you would like to see the impact on cities. So this is the next slide, please. And the problem is that, and this is really for climate very, very important, is that, okay, you have a station, okay, but then the environment surrounding the station is maybe changing. Okay, so if the surrounding is changing, for example, this will affect the observation you are doing. For example, if you have your station in a rural area and then this area has been urbanized with time, this is what happened to our station, is that the station was in a rural area, and then with time, Brussels grow, and then the city, this station is within the city. So it is now observing also the urban heat island. It's not observing only so you have some, what we call the environment change. This is so to detect temperature trend, one has to measure humidity as well, because in the moisture, and then you compute this, because you see, the way the humidity is changing affecting the temperature. So if you have more urban, it means you have less vegetation, okay? If you have less vegetation, means you have less moisture. You don't have moisture, it's more urban. So if you have less moisture, the temperature will change. This is what is here. So we need to know we call this metadata. So if you have the observation, the data of the observation, but you have the metadata of the station. You need to know how the environment change of each station. If you need to take into account. Next slide, please. And this is what we call homogenization. So we need to homogenize the time series, because for climate we need long time series. Okay, long time series. But long time series means the station has been relocated. Maybe the station, the instrument has been changed. A lot of things has been changed for the instrumentation, for example. So you need to homogenize this is relocation of instrument, change of the instrument, change of the surrounding of the shelter. So all this should be taken into account if you would like to use observation for climate. It's not easy. The model is not easy, but also the observation is not easy. Next slide, please. We use also this type of measurement for precipitation. Okay, I show you temperature, but this is also for precipitation. Next slide, please. Wind speed, we use also this type. I see in Professor Surab here will also make some measurement of wind speed here in the campus. Very good. There is a standard, is that it should be at 10 meter from WMO, but it should be also 10 times far from the obstacle, because the wind is very sensitive to the obstacle. Wind is very, very sensitive. If you put obstacle, the wind will be reduced very well so you will not measure 10-meter wind as it's in a rural area. It's really very so that's why WMO we cannot put this in cities. It's impossible, because it's not standard to put this in cities. But now, if you would like to study the city, you need to put this into city to study what is the impact, because the wind will be reduced in city because of the obstacle. So you have much more less wind in the city than in the surrounding because of the obstacle. Next slide, please. We use also this, what we call radio sound. Okay, so this is balloon we put into the atmosphere, and then it gives you the profile of the atmosphere. Okay, it's not the same time. It will be, because it's going with time, it changes, but it gives you the profile of we use this also to evaluate the vertical profile of the atmosphere, if it's correct. Yes. We can use also radar. So this is Belgium here. We can also radar observation. I'm sure you have also radar here, observation. But this is used. We don't use this for climate, because the radar is not a good estimate of it just gives you the pattern of observation. This is really good. So it gives you where are the observations. But the quantity of precipitation is not very well by the radar. That's why now you see people combine with rain gauge. So you combine radar with rain gauge, you can have some good estimate of the precipitation. But radar only is not, the pattern is good. The pattern can be used. Next slide, please. And finally, we use also satellite. So this is Severi. So we put this instrument on the satellite, we launch this, and then this will give you some observation. If you go to the next slide, please. Yes, this gives you the S0. You remember S0, the radiation? I told you in the 1000. But it is 11 years. So this is how the solar irradiance, this is constant normally, but it changed a bit. You see here how it changed. We have a cycle of 11 years, how the solar radiation changed, cycle of 11 years, and this is by this, it's satellite, give you this picture. And it can also give you, for example here, this is I think infrared radiation. So you can also estimate this from satellite. The problem of satellite is that you can, for the moment is okay, but before it's not a long time series. So you need long observation, and there is also problem of homogenization in satellite. So all this, you should take this into account for if you would like to study this. Next slide, please. Yes, and this is the, we can also observe CO2. This is the atmospheric CO2 at Mauna Loa Observatory. I don't know if you know where it is, this. It's in the middle of, I think, the Atlantic? Or? Pacific, yes, thank you. So it's, normally it's there because it's really far from, from anthropogenic. This is really good to measure the CO2. And this is how the CO2 is increasing. And I only, there is a recent, I just put this because, but there is a recent observation. The only way to explain this CO2 is anthropogenic. We did not find, for the moment, any other reason why this CO2 is increasing, except the fact that it is from the anthropogenic emission. Next slide, please. Okay, so the observation, and yes, we also use the reanalysis. What is the reanalysis? This is really very well used. So you can have GFS that Subimal showed this morning from America. You can have ECMWF, it's ERA 5 now. Some people using ERA 5 or ERA interim. This is from European Center. What is this? This is a combination of observation and model. So they combine both observation and model, and they give you for example, ERA, the latest one, ERA 5, is from 1950, I think, until now. You have really a good estimate of the atmosphere. Now it's every hour. So every hour you have the vertical and then you have the surface. You have really every hour. So you can use this to make downscaling. People are using this to make downscaling over India or over other regions. You can use it to force hydrological model. You can use it to force different, you can use this. It's really the best. It's not observation. It's a mix between observation and model, but it gives you the best estimate of the state of the atmosphere. So a lot of people, we are using this to evaluate the climate model. So when we run climate models, we compare with ERA, with reanalysis, to see if the model has a bias. Because every model can have a bias, warm in temperature or dry bias in precipitation, etc. Next slide, please. Yes, just to finish, this is how the model has changed. This is from the IPCC. So this is in the 1990. So this is the first assessment, and this is the latest one, 2021. So check now, let's start by the model. So these are the climate model. So in the 1990, IPCC used only global model, but now we are using global, but also regional model. What is regional model? The same like global, but for only one region. So you run it over India only. You run it, but then you need the lateral boundary condition, but this is another story. I can explain you later. So here what we call Earth system model, and here it's high resolution model. You see here it's 100 kilometer, but the regional is 25 to 50. So we are increasing the resolution. So these are the process that was, you see, we have circulation, ocean, radiative process, land physics, sea ice. You see here we have more, atmospheric chemistry, for example, land use and cover change, land and ocean geochemistry, aerosols and cloud interaction. So we have more process. So the more process you add, the more accurate you are closing to the reality. Now, for the observation, you can see, for example, how many observations? 1887 stations in this period. Look now how much? We have 40,000, you see? So you see the difference of the number of precipitation, number of stations that we use to, there is other change, but this is just to give you what is the evolution of IPCC model and observation. Next slide, please. And thank you. So this is for the first lecture.